Oh gosh, I'm live. I apologize for being a little bit late this week. When you're working from home, you're not always in full control of your situation. But this is the second module for this week. That's module 10. It covers the Kenny textbook, I think chapter 21 on logic and the foundations of mathematics. So I'm going to try and give you a little bit of context for this particular chapter, but I'm not going to go into all the nitty-gritty detail. There'll be some detail and some mathematical logic, but either the again my test questions will be based on the slides more than the textbook. So if you don't have the textbook or this particular chapter seemed really difficult, go by the slides for your exam prep. Let me just say that. Oh, I think we have another quiz this week as well. We have quiz number 3. So have a look at that, start thinking about your papers, and yeah, and if there's anything I can do for you and you're watching live, uh, you could just submit a question through the chat box. I'll keep an eye on it, or just send me an email, or head on to the discussion forums. So this week we're talking about the revolution in logic. What does that mean? What is logic? Well, often we use the word logical to mean something that's just kind of generally reasonable, but in philosophy, logic has a very specific meaning. Logic has to do with the patterns of valid deductive inference, and I'm going to explain what that means over the course of this video. Now, to understand logic is you really have to begin in the context of Aristotle's philosophy. So we talked about Aristotle way back in the first few modules. So let me just give you an overview of Aristotle's logic, which is something we did not talk about when we initially discussed Aristotle. So what's really interesting too about Aristotle's logic is that though it was written in the 4th century BC, so we're talking more than 2,000 years ago, they were considered the definitive words on the subject. Kant himself, who was active in the 18th century, so we're talking like 2,000 years later, believed Aristotle's views were definitive, right? Nothing had been added of significance since. You can actually still find people to this day that argue that Aristotle's logic is the only correct logic. I think Ayn Rand has that view. But, Ayn Rand, between you and me. So it's not exactly true that nothing happened in logic between Aristotle and the 19th century. Medieval theologians made contributions to logic. Stoic philosophers made contributions. But our understanding of logic until the late 1800s was basically Aristotelian. It was basically Aristotle with some slight modifications. So let me just overview Aristotle's logic to explain to you how we kind of took that logic and expanded on it. Because I know what you're thinking. You're thinking logic is just logic with a capital L. How can there be different logics? How can you improve on logic? Hopefully that will become more clear as we move forward. So logic is not concerned just with what's reasonable, with what's rational, with what kind of the relationship between evidence and belief. Logic is something far more abstract. It's something far more mathematical. Logic is concerned with the patterns of correct reasoning. Right? So in the context of this class, don't use logical to mean, well, that makes sense. Logic is something really specific, the forms of reason that can lead us from true premises to a true conclusion. And in logic, what's critical is that the form of reasoning, the pattern of the reasoning, is more important than the content. We're going to separate out the form from the content because a good logical pattern, logical form, should be valid, should kind of work no matter what it is we're talking about. So what is a good logical pattern? It's a pattern in which that if the premises are true, the conclusion is also true. If the premises are true, the conclusion is true, no matter the topic. Right? It could turn out that the premises are false in some specific argument, but if they were true, the conclusion would be true. Now, here's an example of a pattern of reasoning. This isn't an Aristotelian pattern. And there's a reason I'm going to talk about this one first, actually. Suppose I say something like, look, either the butler did it or the maid did it. Premise 1. It was either the butler or the maid. It wasn't the butler. therefore the maid did it. What I'm arguing, right? Premise one, either one or the other. Second premise, it wasn't the one, so it must be the other. So this is a good logical argument. It's a good argument because the conclusion follows from the premises necessarily. If the premises are true, the conclusion is also true. Now, of course, I could be factually wrong about the truth of the premises, but that question is not a question of formal logic. Logic is going to be about the pattern of reasoning implied by the argument that's behind this kind of argument. If it's true that it's either one or the other, but it's not one, it has to be the other. Then that's just going to be true generally, no matter if I'm talking about butlers and maids or any other thing. Right? It's either, suppose your internet goes down, right? It's either the router or the modem. It's not the modem, so it should be the router, right? So it's either one or the other. It's not the one, so it has to be the other. If the premises are true, the conclusion has to be true. And that's a fact about the pattern of reasoning and not a fact about the modem, the router, the butler, the maid. Right? So the pattern of reasoning we can abstract a little bit and replace butler and maid with things that all look like variables, like in math. Generally speaking, I can say either A or B is true. A is not true, therefore B is true. And A and B stand in for butlers and maids, modems and routers, whatever it is. Right? But the pattern here is what's logically valid. No matter what you put in the place of A and B, it will give you a valid argument, one where the truth of the premises will guarantee the truth of the conclusion. Of course, the premises in a specific argument could be false. The only guarantee formal logic will give you is that if the premises are true, the conclusion will also be true. That the conclusion logically follows from the premises you're given. Right, so there's kind of two, when you're engaging in a specific argument, there's two things, right? There's the validity of the argument, the pattern of the reasoning, and the actual truth of the claims you're making. Logic is only concerned with the pattern. So why was Aristotle so significant? The genius of Aristotle is that he systematically investigated patterns of reasoning. And in doing so, he tried to list only the good ones, to separate out the good patterns from the bad patterns of reasoning. He wanted to have only those arguments that would lead us from true premises to true conclusions. But how could he give us a list like this? Aren't there infinitely many arguments? Well, yes, but no. So what he did is he restricted the way in which you could construct an argument. So he elaborated like a basic schema, like a mold all arguments had to follow. He called this the syllogism. The syllogism always has two premises and a conclusion. The statements were tied together using all, some, none, and is. So you could think of it as kind of a logic that really captured the idea of membership in classes of things. So here's a specific example using the syllogistic form. Two premises, a conclusion, and then these kind of quantity and relation words like all, some, none. So if I say premise one, all whales are mammals. Everything that is a whale is in the category mammal. Then I say Mr. Splashy Pants is a whale. So if Mr. Splashy Pants is in the category whale and all whales are in the category mammal, logically, Mr. Splashy Pants is a mammal. So this is a valid argument. It's valid not just because the premises are true, but because the form of the reasoning is valid. No matter what I talk about, it doesn't matter. I'm talking about whales and mammals and splashy pants, but it could be about anything, and the argument would still be valid. That's the kind of insight here, right? Here's valid and invalid arguments. An invalid argument does not lead you from true premises to a true conclusion. It could lead you from true premises to a false conclusion. So here's a valid argument. All humans are mortal. Everything that is human is in the category mortal. Nick is in the category human, and all humans are in the category mortal. Therefore, Nick is mortal. It's true. I will die one day. Woohoo. All right. Here's an invalid argument. Same first premise. All humans are mortal. Mr. Splashy Pants is mortal. Therefore, Mr. Splashy Pants is a human. That's invalid. Splashy Pants, we've already established. Mr. Splashy Pants is a whale. So what went wrong? Why is the second argument not logically valid. How did we get from true premises to a false conclusion? Because it's true. All humans are mortal. True. Mr. Splashy Pants, the whale is mortal. True. Mr. Splashy Pants is human. False. What happened? Well, what happened, of course, is that there's a difference here. Right? Here the premise, too, is different. In the valid argument, Nick is a human. All humans are mortal. So we're referring to the first part of this first premise. Here we're referring to the second part of the first premise. Mr. Splashy Pants is mortal, but there's lots of mortal things. There's some non-human mortal things. Therefore, the conclusion is invalid. You could draw like if you've done this in math class in high school, you could draw a Venn diagram, right, which would tell you why exactly this argument went wrong. So what Aristotle did is he investigated all possible combinations of his schema, of his structure. And he did one by one, checked them to see whether they were valid or invalid. And valid just means if the premises are true, the conclusion is true, in a general sense, if you replace it with variables. For Aristotle, there are 256 possible combinations of his terms. There's 256 roughly possible ways of putting together a syllogism. Of the 256, only 24 are valid. Right? So he systematically investigated logical form, created a schema, explored the entire space, all the possible arguments, and systematically went through all of them to determine which ones were actually valid. However, there are serious limitations to the syllogism of Aristotle. Right? You might argue, however, I mean, this was a super important piece of philosophy to have done. Like, nobody had done this, right? But there were some limitations, and they were hard to get around, right? One problem is that there are forms of valid reasoning that are very hard to translate in the syllogistic form. One of my earlier examples was either A or B, not A, therefore B. That's actually pretty hard to put in a syllogism. Another one that's really hard to kind of adequately, and people have heroically tried, is a transitive relation, such as, right, this argument is definitely valid, right? If A is taller than B and B is taller than C, then A is taller than C, right? So if Albert is taller than Bob, Bob is taller than Charlie, then Albert is taller than Charlie. That makes sense, right? A is taller than B, and B is taller than C, then A is taller than C, right? That just makes sense. This is very hard to capture into the syllogism. What we need, as these limitations became more apparent, is a more general logic, one that is less restrictive, that is not created solely by quantifying membership relations. All is some, none are, these kinds of membership relations, and is not restricted to a form where there's two premises and a conclusion. We need something more general, capable of expressing more, not so limited by the Aristotelian schema, which is what started happening in the 19th century after a few thousand years. So I'm going to focus on Frege and Russell in talking about the new logic here. There's a lot of people making contributions around this time, right? There's obviously Boole, there's Babbage, there's Lewis Carroll, of all people, making contributions. Ava, so there's a lot of people, but I'm going to focus on the kind of main philosophers who are working on the philosophical implications of this slow revolution in logic happening in this kind of in the 19th century and early 20th century. A lot of the motivation here was actually to work out a proper foundation for mathematics, because mathematicians knew that a lot of their theorems kind of worked, but there was no like grand unifying theory of mathematics that kind of explained why it all worked and why all of modern mathematics was on a secure and valid footing. This was, again, I don't mean to get too nerdy and technical about this, but the really two big motivations I would say here were work on infinitesimals, which seemed a little bit divorced from the rest of mathematics, and Cantor's diagonalization argument, which proved that there were different orders of infinity. That also kind of like seemed a little weird. Cantor, you can look up these arguments. Cantor's proofs about infinity suggested that there were some infinities were bigger than others. So the infinity of the rational numbers, for example, is actually strictly speaking larger than the infinity of any natural numbers sequence. So what we have is some motivation to kind of put all of this modern mathematics on a secure, unified footing. The way to do this was through logic and set theory. Of course, the project of putting all of mathematics on the footing of logic and set theory itself suffered some serious setbacks in the mid-20th century, but this was kind of one of the really deep motivations here for creating a more general logic. So what Frege and others were working on was something called propositional logic. So the insight here is that claims, any kind of statement, could have not any kind of statement. Some statements could have truth values. And sentences capable of having a truth value, things that would be either true or false, like in other words, not questions, not exclamations like ouch, but something like the sky is blue, or water is wet. These statements could be either true or false. And if we represent sentences or statements or propositions, which is kind of the technical term we use, if we could represent a proposition by a variable, and that variable could have the value of true or false, then we can build more complex sentences from these basic ones. If you think about the British empiricist view, right, that we start with elementary simples and we build up more complex structures from these, right? There's very much a continuity between British empiricism and logic here. So let's say we have two statements, two propositions with truth values. They could be true or false. And these two propositions are, this week is difficult and logic is boring, right? So we have W and L. So if this week is difficult is true and logic is boring is true, then the sentence, this week is difficult and logic is boring, can be written like this: L and percent and L and W. So what a logician would say is that if L is true and if W is true, then the sentence L and W is also true. Because, generally speaking, any sentence of the form X and Y, where X and Y are any truth value proposition whatsoever, right? Sentences of this form are true when both their components are true. So the value, so what's really happening here is that we assume the propositions L and W have truth values, and then we assume the connective, the and, also has a truth value itself. We can think of the and as being true when both of its components are true. Now, if you've taken a computer science 101 course, you're just thinking, oh my gosh, this is just a logic gate. Basically, yeah. Propositional logic or sentential logic, a Boolean logic, whatever you want to call it, however you trace that history, is really the fundamental theoretical underpinning of a logic gate in a computer. And if you know how that works, right, then you're going to find this very easy to grasp. If not, we'll work on it a little bit more. But really, it underpins almost all of the 21st century, right? Because my cell phone here is all logic gates. Fundamentally, it's processors, microprocessors. So viewing propositional logic as statements with truth values, with connectives, bringing them together to more complex sentences themselves with truth values, leads to a very general logic that can do a lot more than Aristotle. Let's go back to our butler or maid argument. Either the butler or the maid did it, either B or M. It wasn't the butler. So here I have sentence B, it was either the butler. Sentence M, it was either the maid. I have a connective. Either B or M is true. It wasn't the butler, not the case that B. In other words, B is false. Conclusion, the maid did it. Right? This argument is a valid formalizable argument because denying the conclusion entails contradicting one of the premises. Right? Let me just work backwards from conclusion to premises here, right? Suppose I say, so the maid did it. Could this be wrong? Could I have made a mistake in my logic? If this could be wrong, then it should be possible that the maid did it is a false statement, not the maid. So if it's not the maid and it's not the butler, then either the butler or the maid has to be false. Or not butler has to be false. In other words, if I say the conclusion is false, what I'm really doing is denying one of the premises. Right? It's impossible to deny the conclusion without also denying a premise. Right? That's how I know it's valid. Denying the conclusion is also denying a premise. Now, you might think to yourself, okay, that's all nice and well, but there's a really important element so far. Right? You gave me a sentential logic, a propositional logic, I have connectives, but didn't Aristotle have something else? What about these terms? Some, all, none. Those are so prominent. Frege so we're going to call these quantifiers. And Frege introduced them by distinguishing between properties and things that can have a property. And that's how we are going to reintroduce quantifiers into a more general propositional logic. I mean, if another way to think about it is, actually, no, let's not do that yet. So for example, take the number 4, which is an even number, right? There's even and odd numbers. Even numbers are divisible by 2, odd numbers are not. So 4 is an even number. You can think of the object 4 as having a property, being even. So a quantifier, its job is to say that some class of objects have or don't have some property. All right, I can say all multiples of 2 are even numbers. So by making a distinction between objects and properties, we can make statements about membership in classes or sets. That gets us set theory and the foundations of mathematics, which I'm not talking about. But we can have this kind of general way of talking about quantification, which Aristotle had, and propositions, which Boolean logic had, and then combining them and having a logic that's really the best of both worlds. We have Aristotle's logic and propositional logic. So if I say something like the Aristotelian premise, all humans are mortal, what I'm saying is for any object X, for any object that I'm speaking of, if X has the property of human, then X will also have the property mortal. And that's how I'm going to turn the Aristotelian quantifier into a statement about objects and properties. Right? Any object with the property human will have the property mortal. Frege's new logic was in fact better than Aristotle at talking about quantification because you can have expressions with multiple overlapping quantifiers. And you could be really precise in the expression of these things. For example, you can't say this using Aristotelian logic very easily, right? Some cat is feared by every mouse, right? Or every mouse fears some cat. And then you could prove that certain conclusions logically follow, like all mice are afraid of at least one cat. And back when I was teaching at Western, I used to teach the logic class, and we used to do all the fun little equations on the blackboard because we're not doing this in English. I'm teaching you this stuff in English right now, but what it actually looks like when you're working through the system is it looks like a bunch of math on the blackboard. And it's really fun to teach because you have very much the kind of Hollywood trope of writing these equations on the blackboard and like looking, like a bit of a mad scientist. So it was a really fun class to teach. I've been trying to get Fanshawe to teach a formal logic class, but they're kind of like, I don't think we really need to put the students through that. So as I said, Frege's goal was to use his new logic, his very general propositional plus quantifiers and logic to formalize and give foundations to mathematics using his logical axioms alone. But there was a problem. And Bertrand Russell, the great British analytic philosopher, was the first to spot a flaw. And this flaw is really at the heart of all mathematics now. You can't eliminate it. And it's a very beautiful flaw in a way. Um, so Russell was amongst the very first to understand the implications of Frege's work. We're 30 minutes in? Okay. But he realized that the logical axioms Frege had given for mathematics actually contained a fatal contradiction. So as I've explained, Frege's system gave a really general language to express membership and quantification. So we can think of that in terms of sets of things. So the set of all even numbers, the set of all odd numbers, the set of all prime numbers. So I can define sets as containing members specified by a certain logical function. And just simplifying a little bit, we can also specify logical functions that include the possibility of self-membership. So think of the set of large things. The set of things that are big is itself big because there's many big things. So as I'm imagining a set. I'm putting in my basket all big things: an elephant, planets, skyscrapers. And this collection is getting itself very large. So then I have a question. Is the collection of large things itself large? If it is, it has to be in its own collection. Well, yeah, it's going to be in its own collection because the set of large things is itself a very large thing. So it is a member of itself. Now, some things, right, some sets are going to be members of themselves and some are not. Like the set of small things is not a member of itself because it is itself not small because there's many small things. So it doesn't apply to itself, right? Go back to Plato and Aristotle, right? The third man argument proposed an infinite regress on exactly this issue, right? Because for Plato, the set of blue things had to be itself blue. And if the set of blue things is itself blue, then it's a member of itself, and it's a member of itself. You need another form accounting for the set of all things that are blue plus the idea of blue. So it is really all philosophy is Plato and Aristotle arguing for thousands of years through us. Because Bertrand Russell said, look, define the set. Here's a set. Imagine the set of all sets that are not members of themselves, right? So large is a member of itself. So it's not in it. Small is not a member of itself. So it is in the set of all the sets that are not members of themselves. Right? So again, I'm imagining I have a basket. It's a basket with smaller baskets in it. In this basket, I'm putting everything that is not a member of itself. The basket of small things goes in. Whoop. All right, the basket of blue things goes in because the set of blue things is not itself blue because sets don't have color, right? So now the question is, I'm the set of all sets. Take the basket containing baskets. What does it contain? All the sets that are not members of itself. Is this basket that doesn't contain members of itself, is it itself a member of itself? Well, either it is or it isn't. If it is a member of itself, then it shouldn't be in the basket per the definition. But suppose it is not a member of itself, then it is. Though it's neither a member or not a member of itself. The property leads to contradiction. All right, because if it is, then it isn't. And if it isn't, then it is. We got a bit of a problem here. Okay, forget the sets that are members of themselves. Imagine there's a city. And in this town, there's a barber. And you go to the barber shop, and the barber, of course, shaves all and only those who do not shave themselves at home. Does the barber shave himself? Right, he shaves only those who do not shave themselves. Does he shave himself? Well, if he does shave himself, he shaves only those that do not shave themselves, so he doesn't. But if he doesn't shave himself, then he does. All right? uh-oh, these are all logical paradoxes of self-reference. The Greeks knew about these paradoxes of self-reference, and one of the issues with the generality of the new logic is that they were so general, they allowed you to express so many different logical statements. You were also able to express self-referential statements. And self-referential statements, though they're grammatical in the system of logic, are contradictory because they create a paradox. The liar paradox is probably the most famous and earliest of these, right? A man says that he is lying. Is what he says true or false? Right? Or think of the simplified version as, of course, this sentence is false. This sentence is false, right? If this sentence is false, it's saying something true. Because if it's actually false, then it's true that because it's saying of itself that it's false. So it's true that the sentence is false. But if this sentence is false is true, then this sentence is false is not actually saying something accurate. So it must be false. So this sentence is false is making a false statement. But if this sentence is false, then this sentence is false must be true. Oh my gosh. Now we have a big problem here, right? So we're kind of looping in on ourselves. If this sentence is false, is either true or false. If this very sentence is false is true, is making a true statement, then this sentence is false can't be saying something true because it says of itself that it's false. So it must be false. But if this sentence is false, it's saying of itself that it's false. So it's not true that this sentence is false, therefore the sentence is false, so it's true. Oh my god, my brain's gonna explode. Oh! Right, so how do we deal with the paradoxes of logic? You know, there's some suggestions. Bertrand Russell and others suggested something called type theory, which says that you actually just kind of ban self-referential statements because sets containing sets are just kind of firewalled off from each other, is the idea. And that you can't actually, a higher level statement can't make statements about lower level statements. Right? You just kind of firewall them off using Ramsified type theory or whatever, and then you just make them ungrammatical. You just kind of rule them out. A lot of people don't like these solutions. So, I mean, if you're interested, there's a lot of literature, but it's not all math and logic all the time. I think if you're interested, if this paradoxical stuff is really blowing your mind, you know, you should read about Kurt Gödel and the incompleteness proofs, which basically suggested that any system attempting to give you an adequate account of even basic arithmetic is going to have to make a choice between statements that can't be proven true or false, or statements that can be proven to be contradictions. So you can have inconsistency or incompleteness. Pick your poison. Most mathematicians pick incompleteness. Right? They're more comfortable having mathematical questions that can't actually be solved. Some very vanishingly small minority actually are okay with contradictory systems of logic, but Graham Priest aside, these are very small. It's a very small kind of niche topic to work on. So apart from work in Logic and the Foundations of Mathematics, Bertrand Russell and Frege and others applied this to language because they thought of their logic as a form of language. And maybe we can understand the language we speak, English, French, Mandarin, whatever it is, as a kind of a logical system in and of itself. And hopefully, logical analysis of our language could help us be better at dealing with philosophy. So let me just look at a couple of examples here before I close. How am I doing? 40 minutes. Mill, who you might remember as a utilitarian, also wrote a little bit about language and logic. He was interested in how meaning works. So he had a theory about the meaning of a name, saying that the meaning of a name in a natural language is what it refers to. Right? So what is the meaning of Obama? The meaning of Obama is it's what it refers to, which is the individual in the world Obama. But Frege noticed a weird problem, because the meaning can't always just be the reference, because you can substitute names that refer to the same thing, but not preserve the meaning. So the meaning and reference come apart. So for example, right, Bruce Wayne and Batman, fictionally, right, in the Batman universe, refer to the same entity, right? So the meaning of Bruce Wayne and Batman have to be different, right? Because even though they refer to the same thing, sentences using Bruce Wayne and Batman don't mean the same thing. So, for example, Gordon knows Bruce Wayne is Bruce Wayne. Well, that's not even worth saying. Of course, he's himself. Gordon knows Bruce Wayne is Batman. Well, one could be true and the other one false. So you can't. So meaning can't just be exactly the same as reference. So Frege says, look, in natural language, you need to distinguish between the sense of a word and what it actually refers to, because the meaning of a name goes beyond what it's pointing to in the world. So that was kind of an interesting logical point about language that Frege was making. So for some words, it's kind of, easier to make the case that the referent and meaning are closely tied together. Russell was puzzled about things like the King of France, which is a description. The meaning of the King of France definitely can't be the referent here. There is no referent. There's only a sense of it. And Russell thought that an expression could have a logical structure and that the language of logic could help us understand the meaning of our terms, because meaning can't just be reference for a number of reasons. So you might think that the meaning of a description has to point to an individual, but Russell disagrees. He's going to say it's actually the meaning of a description in our language, like the King of France, is actually a logical function. It's not the same as a name that points to an individual, right? For example, the Prime Minister of Canada doesn't mean Justin Trudeau, right? It can't. The Prime Ministers change. The Prime Minister of Canada can't mean any specific person. It means the unique individual who has some properties, whoever happens to have that property, right? This picture over here has a number of distinct individuals who have satisfied the properties Prime Minister of Canada. All these people at some point have been Prime Minister of Canada. Here's another puzzle. I feel like I've lost everyone now. So if I say the King of France, there is no King of France. France hasn't had a king since 1789. But if I say the King of France is bald, and it is not the case that the King of France is bald, these are weird because these sentences seem to violate a logical law, the law of excluded middle. Sentences are either true or not true, right? So if the King of France is bald, that's either true or false. It is not the case that the King of France is bald should be either true or false, but they seem to be both false. But how could something and its negation be true? Right? The law of excluded middle says, right, for any statement, if the statement is true, then its negation is false. And if the statement is false, then its negation is true, because there's only two truth values. Right? So how do we preserve logic in cases like these, Russell asks. So Russell proposes that there's really kind of a hidden logical structure to our everyday languages. And this is really interesting to me because we start getting to like more modern linguistics of like deeper structures of language, which we might be doing in our brains. Who knows? So when I say the King of France is bald, what I'm really saying is there's a claim. There exists a King of France, and that king is bald. And what we don't notice is an ambiguity in natural language. Right? There's two different negations. I can say it is not the case that there exists a unique King of France and that king is bald. Or there exists a King of France and that king is not bald. Between these two ambiguous readings, N1 is the appropriate logical negation that preserves excluded middle. Right? There exists something. It is not the case that there exists something. Right? There exists a unique King of France is false. Right? It is not the case that there exists a King of France. That's true. Right? So we have a negated claim, and an unnegated claim, one's true, one's false, and we've kept excluded middle. And this is not the right logical negation here, which is why we have to be careful about the structure of our logical assertions, Russell says. If you're, as I've said earlier, I used to do this class in the kind of proper mathematical way. It took 2 semesters. We would start in September all the way through April. And at the end of April, the students should be able to read and understand this modern notation here, right? That the King of France is bald. So just to break it down, this is a mathematical operator that means there exists something. What exists? There exists an x. And what is that x? It has the property of being the King of France. And for any y, any object at all, if y is the King of France, then x equals y. So this is a uniqueness condition, right? So there exists a King of France, and for anything that is the King of France, the one thing that exists is it. So that's just saying there's only one, and it has the property of being bald. That particular King of France has the property of being bald. All right, so this is easy, kind of a fun thing that only takes about 2 semesters to learn. But that's kind of what it looks like in modern logical notation. And the idea, again, the basic idea, I'm not going to ask you this in an exam. Just that the basic idea is that we can analyze natural language, the languages we speak, using logic to be clear about meaning. That's really the only claim that I want you to remember. We can use logic to understand with more precision the meaning of our terms. Okay. Why is this important? Because logical clarity and precision, these analytic philosophers claimed, philosophers like Frege and Russell, would eliminate all confusion. And confusion is the cause of most philosophical puzzles, right? Meaningful statements about entities like the King of France or the Golden Mountain, some thinkers believed, like Hegel, Meinong, who we didn't talk about, to imply that they must exist in some sense because we talk about them, and if we're talking about them, we must refer to them, and if we're referring to them, they must exist in some sense. But Russell used logic to show that sentences about entities don't imply they exist. They follow the normal laws of logic. They follow excluded middle. What they really are disguised existence claims about clusters of properties that may or may not be satisfied. So we don't need to have weird ontologies, weird metaphysics to explain how we're talking about non-existent entities. And it was logic, they claim, that help us, clear up these puzzles. So that's the relationship between logic and philosophy for Russell. Okay, I hope I didn't lose you guys too much. This is some of my favorite philosophy to teach, to think about, to work on as a grad student. So if you're interested, I could definitely point you to some more literature. Otherwise, sorry I'm late. Thanks so much for watching, and I will see you guys on Tuesday.